Hi. So this is a presentation that we update all the time, but specifically here we had a slightly different outline. So even if you already saw one of the Docker intros, there should be some new stuff here, hopefully. So first, short intro about me. So as you have guessed or will guess from the accent, I'm French, unfortunately. One of my endeavors at Docker is to put everything into containers. So I put network appliances because I used to be a network guy in a past life. I put virtual machines, I put display servers, I put Docker itself into containers. More on that later. But so I put stuff into containers and I help other people to do the same because that's what we do at Docker. So usually we do the questions at the end, but and usually you are the ones asking the questions, but I want to do things kind of in reverse. I want to ask you just a few questions to get an idea of the feeling the audience. Who has tried Docker already? A few people. Who has tried a real Docker, so on a real VM as opposed to just the outline tutorial? A bit less. Who has installed Docker locally? Okay. Who has written a Docker file and built that Docker file? So I guess we have kind of a few Docker ambassadors here, but most of you haven't been exposed to it yet. Who has an image on the Docker Hub among those few people? Almost nobody. Okay, so we'll try to tell you about the awesomeness of the Docker Hub as well. So this is the outline for today. First, I will have a little bit of history about where Docker comes from, then explain what it is and why it's so cool and why everybody keeps talking about it. Then I will talk about containers, technically what are containers. Then I will talk about the Docker ecosystem, what's around the Docker project itself, then give some kind of Docker ABC to get started with the product, and give an idea of what the ideal container development workflow looks like. So let's get started. History from dotCloud to Docker, because I've been with Docker for almost 4 years, except that Docker is not 4 years old. So the trick is that before being called Docker, Docker was called dotCloud, and it was a platform as a service company. So we were competing with Heroku back then, and then came around people like Cloud Foundry. So that's also platform as a service. The key idea of platform as a service is that you get your code repository, and then you just do something push. So if it's Heroku, you push to Heroku. If it's dotCloud, you push to dotCloud. If it's Cloud Foundry, you push to Cloud Foundry, and then everything happens magically. You have servers that are provisioned automatically, the code is built, and the dependencies are installed. Everything gets copied to that. So as a developer, you can deploy your applications without having to deal with ops ever again. So that sounds like a great idea. We were like the first polyglot PAAS ever, which means we had support for multiple languages before that word was even coined by Heroku. And most importantly, it was built on top of LXC, the Linux container technology, and AUFS, which is a file system technology that I will about which I will talk a bit later. So we were using custom kernels, so it was not something that you could install on your machines. We were operating that on our own fleet of EC2 instances with those custom kernels that were extremely painful to maintain and upgrade. We had ton of patches on top of that so that the container technology and all that came around it could work properly. So it was extremely custom. It was based on a microservices architecture, so when you would push your code, it would talk to a service, then a different service would build that code, that the code would be deployed by yet another service. Resources like containers and load balancers would be managed by yet another set of services. So it was a pretty complicated beast. And more importantly, there was a bunch of components to manage the containers. And the problem is a bunch of components. On each of the machines that was running containers, we had something to create containers, then there was something else to put code into containers, something else to monitor those containers, and yet another component to watch when those containers were using too much disk space, and another for too much memory, and so on and so forth. That was a big problem because all those components were kind of fighting each other when they had to look into our containers. And there were tons of locking mechanisms. We had tons of concurrency issues. We had some extremely embarrassing ones where we're like, okay, this component is updating that container at the same time as this other component, and there is a race condition here. So that was a mess. And so one thing that we decided at some point where, okay, we need to rewrite that container management code. We need to have one single daemon, one single process that can touch our containers. Nothing else will be allowed to touch the containers. If I want to do anything with my containers, it has to go through this thing. That way we can get rid of all the concurrent access and logging problems, and things will be great. We also wanted to have a simpler deployment mechanism because all those components were complicated to deploy. If you have only one complicated component, that's kind of fine. You put that and then you build everything on top of it. If you have half a dozen complicated components just before you can actually start to deploy stuff, that gets more annoying. So that's how we wrote Docker. The first version of Docker was written in Python, and it was docker.py, which is not the docker-py that you can find today, which is just a bunch of API bindings for the current API. So the first Docker code was in Python, and it did more or less what we wanted. But then we were wondering, can we do better than that? Because it's Python, which means it's not Ruby, which means that the Ruby community will never embrace it. Because, I forgot to mention that one of the goals of this big rewrite, of this big refactoring, was to have something open source from day one. Because back in the early days, we say, eventually we will open source that code. So that never works. If you say, well, eventually I will open source that code, it will never be open source because in the first few days of the project, someone will add some credentials in the repository or some code that after just a few weeks will be considered to be too embarrassing to be made public or something like that. So if it's not open source from the very beginning, it will never be ever. So we wanted to change that. We said, okay, we want that stuff to be useful for everybody from the beginning. And so we thought about actually doing that in another language, like let's do that in Ruby. Problem is that we were a Python shop, so we didn't know how to Ruby, and also our engineering team hated Ruby with a passion, so we didn't want them to leave. And let's be frank, deploying Ruby code is just not, that doesn't work. I mean, Ruby and Python are just as bad when it comes to big, complicated deployments. So what if we do that in Go, that new hipster fashionable language? It's not Python, so the Ruby community will be fine. It's not Ruby, so the Python community will still be fine with that. It's not Java, God forbid. It's not Node.js, and more importantly, it compiles to a single, almost static binary. It means that when I work on my Go project, I compile it, I have a single binary, I just give you that binary, you run it, and it works. You don't need to install dependencies. You don't need to install extra packages. You just take that binary, run it, that's it. And in the very beginning of the project, that was game-changing, kind of, because when we said to people, hey, can you test Docker? It's this cool new project we have. They say, oh, what should I do? It's Python? Nah, I'm a Ruby guy. I don't want to look at that. In that case, you just say, this is this single binary. You download it with curl or wget. You run it. It works. And you give us feedback. So that helped a lot. So Docker was reborn in Go in February last year. So that will soon be 2 years. We started with a private repository, which kind of contradicts what I said a few minutes earlier, except that from the beginning, we would kind of talk about people, hey, psst, we have this new container project. Do you want to be in? And if they would say, oh yeah, that sounds great, we would just give them access to the repository. We just wanted to have this small community in the beginning, but very quickly, like 1 month later, in March, we opened that repository during PyCon because, well, we were still a Python shop, so we tried to give something back to PyCon. And so the early Docker project has some very strict requirements. So it was based on Elixir, and you needed a UFS, which is this crazy unioning file system, which doesn't ship with Red Hat distros, only on Debian and Ubuntu, which means that our initial audience was way smaller. So to make things more tangible, I have a little demo of what Docker looked like back then. So I have that's a VM on EC2, and I have Docker installed here. And so Docker looks like this command line thing, and so I will run an Ubuntu container. I do this, and that's my Ubuntu container. So just to kind of prove that I'm in a container, I will check how many packages I have on that machine, 189. Now I will get out of the container and I will check how many packages I have here. And yeah, much more. So I can, if I don't like Ubuntu, let's say I'm old school, I want Debian, it's fine, we have that as well. I think the Debian image is even light, yeah, even less packages. If I don't like Debian distros because, well, I'm an enterprise person, so I want CentOS, fine. I have that as well. Obviously, I don't have DPKG here. I have to use RPM and Yum. If I prefer RPM-based distros, but yeah, we have Fedora and lots of others. As you could see, it was extremely fast to start those containers. And if I want to install something, well, okay, that's not how it works. Maybe something like that. Okay, maybe I need to get update first. Yeah, yeah. So I have a network access. I can do stuff. Once I have made changes, once I have installed packages in my container, I can take a snapshot of that and create more copies of that. So that's what the kind of first contact with Docker looked like. It was, oh, I can spin up those small environments really fast, and that's great. So the community response was huge. People really liked that. Initially, we did that just because we needed a new engine for our PAAS, and we wanted to open source it, so the feedback of the community mattered. But the feedback was so huge that we decided to, little by little, shift the steam away from dotCloud and towards Docker, because people asked for more and more about Docker. So a few milestones. 1 month after the public release, we added some things so that the whole setup would be more automated, so that the list of basic instructions to get started would be smaller and smaller. Then later we added volumes, which was something to be able to deal with storage. We added a real REST API. We added Docker build. This is something I will talk about shortly. We had host volumes, UDP, the privilege mode, which is something so you can run Docker within Docker, VMs within Docker, and lots of stuff like that. Then a very important milestone was 0.7 when we added storage drivers, which sounds like, okay, this is just like some technical details. But actually that was very important because that allowed us to switch AUFS for other storage mechanisms, which means that starting from Docker 07, so in, well, that's almost like the 1-year anniversary of that release, people running CentOS or Fedora or Gentoo, in other words, something else than Ubuntu or Debian, were also able to run Docker. So that was a big deal. Then we added BetterFS, we added support for OS X to run the CLI from OS X. Then another big milestone was the native exec driver. At some point we say, well, okay, LXC was great, thank you. It was one of our basic building blocks in the beginning, but now we want to do the whole containerization ourselves. So we implemented libcontainer, which is something to create containers, but without using LXC. We added so security, so TLS for the API, SE Linux and also security, pause and unpause, and so on and so on. In June this year, we released version 1.0, saying, okay, this is production ready, because before we were telling everybody, Docker is not production ready, use at your own risk. Your house will catch fire, your dog will run away, and terrible things will happen. And many people were using it anyway, in spite of that. Either because they were crazy Russians, and that's only half a joke because Yandex, the Google of Russia, is actually one of the first big enterprise companies that rolled out Docker in production way before it was production ready, just because they say, well, we are comfortable with the code base, and it's either that or running out our own, which will be longer and maybe not as good, so let's use that instead. And then also the first early adopters of Docker were people in the testing industry, because when you test code, if the testing platform blows up, it's not as bad as if you run production code. So yeah, more features, and by the end of this year, you can expect a lot of technology previews around volume management, composition, so running multiple containers at the same time, host management, and so on and so on. So let's compare the initial goals versus what Docker became. In the beginning, it was just a container engine for our PAAS. Containers were really lightweight virtual machines. It was just the goal was to pack as many of them as we could on our EC2 instances, and they were part of a huge, big platform with many components. Now, the tagline of Docker is build, ship, and run any application anywhere. And so let's look into that now, because it's a fancy tagline, but each of those words actually has some extremely accurate meaning. So build, that means we want to be able to take an application and put it in a container. So container is the new package format. Ship, that means we can take that application and now we can deploy it from a machine to another without bothering about the stuff you usually worry about when moving code from one place to another, dependencies and so on and so forth. Run, that means that we can actually run the application. And any application means that this is not only for Java or Python or some subset of the stuff you can run on a server. It's for anything that runs on Linux. And anywhere means that it can run on physical machines, on VMs in public or private cloud, on laptops, and so on and so forth. So let's view each of those things. Build. How do we build applications into containers? So after a while, we came up with Docker files. Docker files are recipes to build containers. The idea is that you start from a base image, like Ubuntu or Debian or Fedora or whatever you want, and then you run commands on top of it. And this has to be really easy to learn, easy to use. We wanted something way easier than writing Puppet manifest or Chef cookbooks or Ansible playbooks or salt grains or pillars or whatever. This should be so easy that if you're just a developer and not a crazy ops person with 10 years of Unix experience, you should be able to write that without a huge stack of Advil on your desk. So this is what a Docker file looks like. Can I point with this? Yeah. So we say, okay, I want to start from Ubuntu 14.04, and then I want to run those commands, and then I have some extra information here. So let's see this in action. So here I get out of this container. I go into this. So I have this exact Docker file, and I will just build it. So I do docker build -t web dot. So this will run each step. So this is running like apt-get update in a kind of temporary container, and when it's done, it will take a snapshot of that container, and then it will restart from that snapshot, and now it's running the apt-get install nginx. Then it will take a snapshot of that, and at the end, it will create a simple index.html file in that container. There we go. Now I will run that container. So, okay, keyboard shortcuts don't work, but that's okay. So I want to run that container detached in the background. I want to publish all the ports of that container so that it's available from the outside. Then I do docker ps, and I see that it's running on that port here, 49153, and I have a browser here, and I just have to add the port. And normally, right, can I zoom a little bit? Yeah, it's really small, but, and there is no way to, I don't know what I did. Right, so now, a very interesting thing about that build process is that we took a snapshot at each step, which means that if I change something in my build, Docker will be smart enough to reuse those snapshots. So let's say I want to say, hi, Kansas City, whoops, I'm in your container, and I want to rebuild that. So now the build will be much faster. See, all the stuff about apt-get update, apt-get install, Docker was smart enough to say, well, I already did apt-get update on top of the base Ubuntu image, so I don't need to do it again. I can just reuse the snapshot. And then I already executed apt-get install nginx on top of the image that already had apt-get update, so I can reuse that as well. However, so you can see here, using cache. However, this line here is new. That's different, because here it's different. So it's say I can't use the caching system anymore, and I'm executing everything from now on. But those big, slow, expensive steps from the beginning, Docker was able to skip them. This is useful because here, okay, it's easy. Just apt-get update, apt-get install one little package. But imagine that here we were pulling down like 500 megs of dependencies and building tons of complicated packages. Then at each build, we are able to zoom through this and still get the advantage of from scratch build recipe. So now I can run that like this. I can do docker ps. It's on the next port. Surprise, surprise. And so if I go to that other port, normally, I see, hi Kansas City, I'm in your container. Sorry, this is really small, but so another advantage of doing things like that is that my old application is still around. If I realize, oh, that's absolutely wrong, I need to roll back to the previous version, it's fine because the previous version is still around. I have not changed an existing server to bring it to the new version. I created a new container next to the first one, and if I want to go back to the old container, it's still around. Here, I even have the two versions running side by side, and typically, if this were like a real application thing, I would set up my load balancers so that when I do a release, I tell the load balancer, okay, now send traffic to that HTTP port. And if I want to roll back, I reconfigure the load balancer to say, well, send the traffic back to the original port. But I still have the two things in parallel, which means I can spin up this new version, do tests, and if I'm happy, then change my configuration while the old one is still running next to it. Okay, so that's the build mechanism that we have. So we take snapshots, we reduce the snapshots, and we can skip over the slow steps. Then we can ship those containers, and the idea is that there is something called the Docker Hub, which is a kind of huge library of container images, and once I have built something, I can put that image on the Docker Hub and pull it from elsewhere. Let's see how this works. So here I will do docker push jpetazzo/web. So this will work because actually before doing that demo, I prepared stuff I did. I logged in the Docker Hub, so that on that machine and on the other machine that I will use, I'm actually logged in the Docker Hub as jpetazzo. And it lets me push that because the image name starts with jpetazzo. If I were trying to do like docker push cerner/something, it would tell me, well, no, you're not cerner, you're not the cerner account, so you can't do that. So I'm pushing that, and so it takes a while the first time, and that's it. And now I can go to the other machine. How do I even do that? Okay. Whoops. And right. So the other is faster. Okay. So that's like a brand new Docker machine. I haven't done anything on it, and now I will docker pull. I will even do wasn't that docker run -d-p jpetazzo/web. And so this could be a completely different distro. This could be running on a completely different cloud. The first one, those two VMs have been deployed the same way because I'm a very lazy person. But the first one could be Ubuntu. The second one could be Fedora. The first one could be a small Docker VM on my laptop. The second one could be on EC2 or some local OpenStack cluster or anything I want. And the whole point is that Docker will figure out the bits that it needs to run that container, and regardless of the host environment, it will get that container up and running so that I don't have to worry anymore about installing packages and dependencies and all that stuff. So yep, it's running now. Whoops. All right, and what's the IP address of the other machine? That's it. Okay, and I don't really know how to copy-paste with the Windows machine, so that's a little bit annoying. And the port number, where was it? 49153. That's interesting, 49153. Okay, I will blame some weird thing. That's the right address. It's running in. Okay. Oh, maybe I need to put HTTP in front of it or something like that. Yes, that's it. No, I don't know how to use a Windows machine, sorry. So I have the right thing here. So one of the whole points, how do I switch back to presentation mode? I don't know. Like that maybe? Nope. View full screen. Yes, perfect. So the whole point is that I did that with a ridiculously easy and simple static web server, but that would be exactly the same thing for an insanely complex web application with tons of dependencies. So the whole point of this build and shipping mechanism is to achieve reliable and consistent deployment. And what we mean by that is that we want to avoid that problem, which is that you have a dev team that puts together some code, then throws the code like above the wall, and then the ops team is like, what should I do with that? And they try to run it, and it doesn't work because they don't have the right distro, they don't have the right packages, a lot of things are missing. So with containers, the dev team can say, you just have to run that container, and the ops team runs the container, and everything is in that image. They don't have to worry about the installed packages, the libraries, the versions, because everything is in here. So next, we said, so it's build, ship, and run. So in the run part, some good news is that those containers are fast and lightweight. So quick demo again, because I love demos when they work. So I will start an Ubuntu container in the background, and another, and another, and another, and a few more others, and that's fast. I mean, can I like benchmark that? Yeah, it takes like 100 something milliseconds to start a container, and they are all running here. Great. That was really crazy fast. Try to do that with VMs. It's not impossible, but it's just that to get VMs that boot in seconds, it's already a lot of work. So to get VMs that boot in milliseconds, good luck. So lightweight. So containers have no or almost no overhead. Some people did benchmarks, and well, benchmarks are just, you can make them tell whatever you want, but so I just show like running a container was fast, but the disk footprint is just about like 100 kilobytes for a simple container that does nothing useful. The memory footprint is like a couple of megabytes. Again, this is much, much, much lower than VMs. This is a benchmark of like InfiniBand throughput and latency, so no difference between native and containers. This is a benchmark to compare how long it takes and how much memory it takes to spin up Apache web servers inside of KVM virtual machines or inside of Docker containers on OpenStack. This is a benchmark of memory speed. Again, containers and physical machines have exactly the same scores, and VMs have a little drop. So just to make things clear, the point is not to say VMs suck, get rid of VMs and let's get rid of those VMware licenses and put containers instead. No, the point is that it's okay to use containers on top of VMs because there won't be a visible overhead to that. So the question is not containers or VMs, it's containers and VMs, because VMs give us all those deployment advantages. So how is it possible to have no overhead at all? The thing is that containers are just normal Unix processes that sit on top of the kernel, and they just have some little labels on them saying, oh, this process belongs to a specific container. And so when that process looks around it to see the other processes and the resources on the machine, instead of seeing everything, it just sees a subset of those resources. So the code path in a container is exactly the same one as in a normal process. Memory performance, there is a little difference there because there is some memory accounting. But the whole point is that whenever you have a small overhead in memory or network or anything like that, it will be first extremely small, like smaller than the VM overhead. And more importantly, if it's something which is a bottleneck for you, you can disable that. Like the memory accounting of container means that your memory intensive workload doesn't work as fast as you want. You can disable memory accounting and have native performance. So the next part of the motto is run any app anywhere. So when we say any app, it means initially we were thinking about server workloads, so web applications, backends for APIs, databases, regardless of what kind of database, message queues, everything that would end up running on some server somewhere. If it runs on Linux, it will run in a container. Then people did some like fancy stuff like let's run a browser in a container for security purposes. Let's run a display server in a container because it's fun. Let's run network appliances. Let's run Docker in Docker, which is actually extremely serious because it lets you do some testing of Docker within a known environment. Let's run virtual machines inside Docker so that you can run Docker within Docker on a VM itself in Docker, and then it gets extremely confusing. And the last part of the motto, anywhere. So when we say that we can run anywhere, so it means Linux servers, regardless of if it's a physical machine, a VM in a public or private cloud, the only requirement is to have a recent kernel like 3.8 or higher. That was a big requirement like 1.5 years ago when we started, but today everything has that kernel, so it's fine. Recently, Microsoft announced that they would also support containers and within the Docker ecosystem. That does not mean that you will be able to run Windows apps on Linux, nor that you will be able to run Linux apps on Windows. It means that you can run Linux on Linux, Windows on Windows, but use the same build mechanisms, the same APIs, the same orchestration tools and frameworks to operate both. So as the ops person, when you will say Docker run 10 containers like that on those machines, it doesn't matter to you if that container is on Windows or Linux. It will be handled exactly the same way. The fine print, currently, officially, Docker runs only on Intel 64 bits, and that's the Intel 64 bits that we know, not the Itanium one of forever ago. Some people have been compiling Docker on other architectures. You can do that. It works just fine. We just don't support it officially yet. You can also run with older kernels, but please don't, because I can't count the number of times when someone showed up to say, well, I'm trying to do stuff with Docker and it crashed. And when I started to like 10 containers at the same time with this and this, and you start to look and say, there seems to be like a nasty bug. Oh, but you're using that 3.2 kernel that is known to have that bug. So please, can you upgrade? So yeah, don't run old kernels. So let's look a little bit like how technically containers are made, what's inside them. So from a distance, containers are like light virtual machines. They have their own process space that you can SSH into a container. You can see the processes. You can have root access, and you can install packages and do whatever you want. But at the same time, containers are just processes isolated from each other. So they don't have all the extra virtualization layers that VMs typically have. Technically, there are two big sets of kernel features that containers rely on to work: namespaces and control groups. So namespaces are the things so that each container believes that it's isolated and has its own space. So there's a PID namespace so that inside a container you just see your own processes, and each container has its own PID number one. There is the MNT namespace, so you can mount file systems inside a container without the other containers being aware of that. You have the network namespace, which means that each container has its own IP address, its own network interfaces, its own routing tables, its own IP tables rules if you want, which is why you can do network appliances within container. UTS namespace, so that they can have their own host name. IPC namespace, that for System 5 IPC, but if I guess that nobody is using that anymore, so that doesn't really matter. The user namespace, so that's to do some mapping between UIDs inside of containers and outside of containers. This is work in progress, but the idea is that you can be user 1000 in the container, and that gets mapped to a completely different UID outside. And more importantly, you could be UID 0, so root inside the container, but outside it maps to a non-privileged user. And then the second big set of features is control groups. So control groups will take care of metering, accounting, and limiting resources. So there is one for memory, so that you can limit the memory of a container, CPU to give priorities to containers, block I/O to limit the amount of data that can be read and written to disks by a container, devices to give fine-grained access to GPUs or special devices to a given container. So that's a little bit like the equivalent of PCI pass-through in VM environment. And then the last thing that made Docker so compelling was that it was using copy and write storage. So instead of say, okay, I need a new container, so I'm going to make a copy of an existing template, we use copy and write. This is why starting containers is so fast, because we're not making a copy of an existing image. We are doing copy and write, which means that we're essentially using a read-only image, but whenever you make changes, the changes are written to a separate area so that the template, the image remains the same, and each container has its own scratch area for writes. And that's why it ends up being so fast to start many containers. This is just a kind of recap of different storage options, but not very interesting. So let's talk a little bit about the ecosystem around Docker. There is the Docker engine, which is the open source tool that I've been demoing, the hub that was involved when I did the push and pull, and then the community and the company. So the engine, it's an open source thing to commoditize Elixir. Commoditize means we want that to be so easy to use that any developer anywhere can use that. It's not anymore something for the ops or sysadmin kind, it's for everybody. It's using copy and write so that it's extremely compelling and fast to use. It's written in Go, so deployment is easy. Everything that I did is exposed through REST API. So when I did Docker this, Docker that, it actually talks to a service running locally, and it makes an API request telling to the service, do this, do that, and that's it. But I could also be accessing remote Docker machines and do exactly the same demo, exactly the same way. It would work just the same. Someday, eventually, I will do the demo from a Windows machine where I do Docker stuff, and it actually talks to remote Docker machines, and it feels like it's local. So we have a builder process, and that's also kind of important because it's part of the whole experience. If we just have the Docker engine and you can start those containers, it's great, but if you can't easily build images, it still means that someone is building the images and someone else is running them. If you've been using stuff like Vagrant, often in a team using Vagrant, there is that person who knows of how that stuff works. They are the one responsible for upgrading the VM images, the Vagrant-based boxes. They are the ones responsible for updating everything. We wanted to get rid of that. We wanted that everybody could be empowered and able to change that stuff. And then there is the container format that lets you share those containers around. And I did not demo that, but under the hood, what we push and pull on the Docker Hub is just simple tarball files. It's nothing fancy, it's no proprietary obscure format, it's just some files. So if you need to build some tooling around that, it's very easy. It's completely open source. Everything, the whole development is happening on GitHub. And all the issues, all the bugs, everything is public, and you can see the roadmap, you can see the currently open bugs and what's happening. You can sometimes see some old bugs and say, well, it's been 6 months and that bug is still not closed, what a shame. But that's okay, that's an open source project, that's how it works. If there is something that is really embarrassing to you, you can fix it yourself and we'll gladly accept contributions. All the communication around the project happens on public channels. We have public mailing list, public IRC channels. And the contribution process itself is very well documented. If you want to contribute a feature, like you say, well, that's nice, but in the Docker PS output, I want colors. That's fine. You can implement that, and the review process explains how it will work. Basically, there will be your code will touch a given area of the code, and there are some persons responsible to maintain that area. And as long as you have 50% of approval among that group, your code gets in. And they are pretty reasonable people. So if your change makes sense, they will happily merge it. Then we have the Docker Hub. The Docker Hub is a collection of services that make Docker more useful. We could liken that comparison to Git and GitHub and Docker Hub. You have Git, it's completely open source. You don't have to give any money to anyone to use it. And then you have GitHub, which is free. as long as you're working on public things. You can give money to GitHub if you have some private code, and it gives you a ton of really great features like the web interface, the pull request workflow, the side-by-side diffs, and so on and so on and so on. We want to reproduce that with the Docker Hub. You can have Docker, you can use Docker and do all kinds of crazy stuff with it without even giving 1 cent to anybody. But there is a Docker Hub that will help to make that experience better. And just like on GitHub, it's free for open source stuff. On the Docker Hub, as long as you have public images, it's free and you only have to pay for private stuff. The community, so more than 600 contributors. That's the only number I want to talk about because the others are probably already obsolete by now. It means that if you take the whole Docker code base, more than 600 people were involved into making that happen. Contrasting to the fact that the Docker company is like 70 people. So if you do the math, it means that less than 10% of the people working on the Docker code are actually employed by Docker Inc., which means that the project is really in the hands of the community. There is no evil central control of Docker by Docker Inc. It's completely driven by the community. People ask us often how we make money. Well, we thought about selling t-shirts and stickers because they're extremely popular, but more seriously, we have SaaS sold to the Docker Hub, like for private images and things like that, and we have like enterprise support offerings and training and all that kind of things. So how do we get started with Docker? Well, we have something called boot to Docker, which is a tiny VM image, like 25, maybe 30 megs now. So it runs on everything, VirtualBox, VMware, Parallels. It can work on Xen, on KVM, or on anything. You can even like put it on a CD or a thumb drive and boot that on a machine directly. And it's a fully working Docker environment. This is not like the lightweight edition of Docker for evaluation purposes. It's what people actually use if they are not using Docker natively on Linux. On Linux machines, we have packages for all the distros out there. If you don't like packages, you can just download the binary and run it because this is Go. We have easy provisioning instructions for virtually all the cloud providers out there. And some people even built distros specifically to support Docker and containers. So then once you have installed Docker, you start to write your Docker file. I hope that the small example I made convinced you that it was really easy. It's not like learning to do Puppet or Chef. Building your app will be fast. You will probably hit a few bumps on the road, but it's pretty easy to get started with that. One thing is that with a Docker file, you're not defining a whole application. You're just defining one component of the application. If you want to define a whole application, then you have to stack containers and use Fig. Fig lets you define your stack of containers into a YAML file, and which looks like this. So basically, you have sections for each service. So in each section translates to one container. So this is a Mesos cluster. And I'm a little bit behind on time, so I won't run that demo, but basically I say I want to have one container running a Mesos master, one container running a Mesos slave, one container running the Vault framework, and then I do Fig up and it works. Well, I can't resist, I will do it anyway, I think. So I go here, I do Fig up, and it brings up my containers, and I see the aggregated output of all my containers, like this is the master, slave and everything, and this is running. And normally if I go to the other machine, I think, and it should be of port 8080, and yep, this is the thing I just deployed. It's so it's a little front end to create more containers, and so it's a more complex application, makes some multiple parts, and yeah. Okay, so in here, in addition, we had a short demo of Mesos, which is usually a big and hairy orchestration framework, so that's great. So the development workflow looks like you do a per project setup, where the first time you say, okay, let's write the Docker files. Let's write the Fig YAML file, test, so make sure that I can go to a completely blank Docker machine, clone my code, Fig up, and everything shows up. Once I have that, I'm good to go. And then each developer that you onboard just needs to have a working Docker environment, and with boot to Docker, it's ridiculously easy. And then they clone the repo, they fig up, and it just works. They have their local copy of everything up and running, including databases and cache and all that stuff. And then basically you edit your code. You can either test locally or in a container. There is a mechanism so that you can share files between the container and the host system. And whenever you want to test in real conditions, you fig up again to rebuild images and run them together. And if you're happy with that, you ship those containers. There are tons of options when it goes to Docker in production. I have a full 45 minutes talk about that, so I won't give details now, but I can address a few specific questions during the Q&A. A good thing to do when you have a Docker workflow is to implement CI/CD. So basically, each time you do some changes, you commit them, and then you want to have hooks so that it builds containers, tests them, and move them to the server. And that's exactly what we do with the Docker Hub. The Docker Hub is not just something to exchange container images. You can also set up something called automated builds, which links a GitHub or Bitbucket repository to a Docker Hub repository. And so each time you push to GitHub, the Docker Hub will get the code, build it, test it, and push the images so that they are available to use. Soon we'll have more interesting features like automated, like possibly security audit of images on Docker Hub, automated deployment. So once the image is ready, it gets kind of proactively pushed to your server so that it's ready to run here. And the Docker Hub Enterprise, which is to have all those features, but behind your firewall on your own servers instead of publicly hosted in the cloud. So the summary is that with Docker, we can put our stuff into containers, move and run those containers anywhere. We have recipes to make deployment really easy for everybody. We have Fig when we need to run multiple containers together. And we have the Docker Hub so that we can share those images and serve as a kind of building blocks for our deployment pipeline. So this a few links for information. So we have IRC channels which are extremely active. So when you have like random questions and a quick Google doesn't turn anything up, you can directly ask them and people usually answer. I can answer to tricky questions if you have some. And so we are soon rolling out Docker Hub on-prem. So the sales team told me that I had to mention that. And so that's pretty much all I got. If you have questions, I'll be extremely happy to answer them. Thank you.
Hi, my name's Aaron. The hardest part I've been trying to wrap my head around with Docker is a lot of times we have like these huge databases, like big data, or even just like a regular database of just like relational data. And how do I move that around with Docker? Or do I not? Do I leave it in place? What do I do to make that go smoothly?
So when we have a big database, how do we move that around with Docker? The idea is that there is volumes that let you separate some things and not get them inside the container copy and write file system. So typically when you run a database, the binaries and the configuration will be kind of in the container and the data will be in a volume, which means that when you will do an update, you will replace that Postgres 9.3 with Postgres 9.4, but the data will be in that volume, and that volume will be conceptually kind of detached and reattached to the new container. So the data doesn't, in that case, you never want to Docker push that 3 terabytes database, obviously. You want that to be on your machine in some well-defined directory, and you kind of plug that into the container. The nice thing is that you can plug that into multiple containers at the same time on the same machine. So when you want to do upgrades to some new version, you can have the data, whatever the data is, available to multiple containers at once.
I had a question. I think you maybe spoke to this a little bit, but just for clarification. So when you're saying, you can run stuff on Windows or Linux or Mac, does that mean like if I'm using boot to Docker on a Mac, for example, I can, use a Docker file, create a container, and then not run that same container on like Linux or Windows with boot to Docker? Or is that incorrect?
You can run the same container. I mean, as long as you're using boot to Docker. Boot to Docker is a Linux VM with Docker in it. So once you have built that container, it can really run anywhere. However, typically we don't have a super fast, awesome upload between our local laptop and production. So typically what we do is that we push the code, and then the containers get rebuilt up in the cloud somewhere, and from that point we can ship them around. So it could be the question like, well, I have that exact version working here on my laptop, and now you're telling me that I have to rebuild in some other cloud VM instance. What's the point? The point is that, yes, that will be a separate build, and maybe it will be slightly different from yours, and that will suck. But the point is that once you have that build, once you test that build, and once it's kind of validated by automated or manual QA and everything, then you can reuse that build and deploy it all over the place. It's very different from the approach where I have 100 machines all running Puppet apply or executing some deployment script at the same time. And maybe that will fail on a few machines because they are downloading packages from something, and one of the mirrors will fail just at that time, and so I end up with like 90% of my fleet is up to date, but 10% not. So containers are a way to help with that. I have my container, and that image will be everywhere. It might not be exactly bit for bit the same as the one I have on my laptop, but it will be the same across all my deployment platform. I will repeat the question, it's okay. Yeah.
Can you hear me now?
Yeah.
Can you describe the best practice for using OpenStack Heat with Docker?
Best practices for OpenStack Heat with Docker. I have an answer, but it's too long to fit in the margin of that talk. The idea when you want to use Docker with Heat is because you want to use Docker together with other OpenStack resources. So I would say first, make sure that we're using the right tool for the right job. So if we have other resources in OpenStack, VMs that we want to use as VMs, databases, maybe we're also using the SDN with Neutron or other components of OpenStack, then it makes sense to use the Heat integration and to have a single Heat template that references containers, VMs, network resources, and so on and so on and so on. Once you are in that framework, I don't think there are really specific things to be aware of. The key thing is to create your containers and think of them as a kind of black box with input and output. When input is what do I need to bring that up? Okay, maybe this is a database, so I need to give it credentials and things to provision initially. And the output will be something else. So for the database, it's exposing some TCP thing, and you just think of putting those things together like that. So in the database example, it means that sometimes you want to give the credentials to the database to tell it, okay, database, please configure yourself. This is the user and password that I want. Sometimes it's the other way around. The database comes up, generates the credentials, and tells you this is the credentials that you should use. So I think when writing Heat templates, it's the kind of thing to keep in mind to understand exactly how the dependency tree of the different resources has to be laid out. And one last question? Or no last question? Thank you.